to this computer. There you go. So first of all, my name is Wenming Yi. I'm a program manager, a product manager at AWS. So I looked after a variety of open source software projects related to deep learning or machine learning. One of them is DGL. So DGL stands for Deep Graph Library. And we have a very talented team in both Palo Alto and Shanghai. So they build DGL for us. I also cover something called AutoGluon, which is a AutoML framework, which is getting a lot of traction within Amazon. So we primarily use that for a lot of our classification, among other, supply chain, among other tasks at Amazon. So, and of course, I cover some of the other tools like Gluon TS or time series neural networks. Quite a bit of innovation and work being done in my team. So we're also looking for interns and full-time folks. So if you're interested, definitely feel free to reach out to me. So this user group is a combined effort between NVIDIA cuGraph team. I have some of the members here. So Xiaoying is one of them and Joe is another. Yeah, and we, at the beginning of the year, we basically looked at the trend of GNNs going up and up. We're seeing a lot of customers are starting to use it in a very serious way, both at scale and also starting to use more sophisticated models from the GNN library. So we decided to start this user group. So Joey, maybe you want to introduce yourself a bit and say a couple of things. I know there's always new folks that are coming to this group.
Right. So I started off, I've been in NVIDIA for about 8 years now, working in sparse linear algebra methods and machine learning. I was one of the early creators of the Rapids package for data management, pandas on GPU plus scikit-learn on GPU. And we have another package called cuGraph, which is network X on the GPU. So we're also adding in cuGraph features into the DGL, the deep graph libraries, to accelerate a lot of the graph analytics and graph sampling processes you need for GNNs. And when Ming reached out to me to start this user group, seems like a great collaboration. We're also looking for people interested in graph analytics and graph neural networks at NVIDIA. So anybody interested, please drop me a line. Thanks.
Thank you, Joe. Without further delay, I want to just go right to the agenda here. So first of all, we have Sergey Ivanov joining us from Moscow, and he is there, and it's 2 a.m. so thank you so much, Sergey, for for agreeing to this talk. And I particularly really liked his paper here, which is GNN paper. I'll let you introduce yourself more properly and also let you go right to your presentation. I'll stop sharing here and you can start sharing your screen.
Sure. Thank you so much, Wenming. Let me share the screen. Yes.
Yeah.
All right. That sounds good. So can you see the screen?
Yes, we can.
Okay, perfect.
Yeah.
So thank you very much for inviting me. It's a pleasure to present my work here. My name is Sergey. I'm a senior research scientist at Criteo working in France. So my research interests are in graph machine learning and recommender systems. And I also run a GraphML newsletter and channels on Telegram. So if you like this field, please do subscribe. I'm trying to popularize and promote some of the recent works that people do in this area. And today I will be speaking about the paper, a clear paper for this year, Boost and Convolve, gradient boosting meets graph neural networks. So we all know that graph neural networks right now conquer the world. And we see a lot of application success stories for GNNs, from self-driving cars using GNNs to simulating dynamics of the molecules, to drug design, to social network analysis. And when we train GNNs, we assume two things. We assume that we are given the graph topology G and also the node features. And lots of work studied how GNNs perform on different graphs. So for example, we know some guarantees on the expressivity of the GNNs, how different GNNs distinguish isomorphic graphs. We know the universal approximation theorem for GNNs, how different GNNs can approximate any function on the graph topology. But not that many works studied how different GNNs perform on different node features, X. And ubiquitous graphs in the literature include, for example, molecules where features are one-hot encoded of the atom type, or the Wikipedia where the features are back of words for each article. So you can see here the X is very sparse, and it's a matrix of ones and zeros. Also, sometimes we see graphs such as OGB archive, where the features are pre-trained word embeddings. So we call these features homogeneous, and they have the same type, scale, and meaning. And GNNs work really well, as we have seen in many experiments on such features. Now, we have other types of graphs, other types of node features. For example, we have the graph of Facebook, where features gender, age, and university of each particular person. We have a graph of houses, where features are traffic, geographical positions, and number of inhabitants per area. Or we have a recommendation graphs, where features are price, brand, last time visits, and others. And we call such features heterogeneous because each feature has its own meaning, and it can be different in data type. For example, it could be Boolean or string, and it has a different scale from others. And as we saw in this paper, GNNs don't work really well on such features. So you have to do other tricks than just applying GNN. And at the same time, one of the common knowledges in machine learning is that graph Boolean decision trees work really well with tabular heterogeneous data. So for example, XGboost or CatBoost, they work really well on tabular data sets with heterogeneous features. However, GBDT work well only on tabular data and not on graphs. So there is no easy way to apply GBDT on graphs. And the main questions of this paper that we ask is, can we combine GNN and GBDT into a single model that works on graphs with heterogeneous features? So can we somehow use the benefits of GBDT in order to improve our performance on graphs with heterogeneous features? And we propose this Boost-GNN paradigm model. But first, I will talk about one of the most straightforward approaches to this problem. So you could first pre-train GBDT model only on the node features X. You get some model F, which would improve the node features for GNN. So for example, you can use this predictions f of X as the new node features for every node. And then you would train GNN on the obtained node features X prime and the original graph G. And you would train separately another GNN, which would make a prediction for every node. And it's very easy to implement because this is decoupled approach. You first train GBDT and then you train GNN. However, GBDT doesn't use the graph structure at all. So there is no signal coming from the graph to GBDT, and therefore it may overfit and it may be suboptimal. So what we propose is what we call Boost-GNN, or BGNN for short. And it builds on this idea. So we first train K-trees of GBDT only on the node features X, and we get the predictions f of X which will augment the original input features for the graph. So as I said, it could be, for example, that we use f of x instead of original node features, or it could be used as additional node features for GNN. And then we make L steps of L propagation, of back propagation for GNN with this G and X prime, and we compute some loss L with the predictions from GNN. And then what we can do is we can take the gradient of this loss function with respect to X prime. And because X prime now includes the information from GBDT, which is f of x, we can pass this gradient to the next batch of trees for GBDT. So the next batch of trees, it will take as input node features x as usual, but it will try to predict instead the gradient of the loss with respect to x prime, which is the first GBDT's prediction. And GBDT works in such a way that it tries to improve the errors that it made during the first steps of GBDT. So GBDT makes some predictions at first, and then all other trees are trying to improve the predictions that made during the first step. And there are some benefits of this approach. In particular, GBDT is great because it has this built-in pre-processing pipeline. So in particular, it works really well with missing values, with categorical features, with features of different scale. So because GBDT is at the beginning of this architecture, you don't need now to have this additional pre-processing for your data. Then we can also work with any GBDT model and GNN architecture. So for example, for GBDT, we tried LightGBM and XGboost models. And for GNN, we tried the graph attention networks, APPNP, GCNs, and other GNN models. The whole architecture is trained end-to-end. So means that GBDT actually gets the signal from the graph, and GBDT is trained together with GNN. It's not a decoupled approach, and therefore it's it better handles the overfitting. And there are two interpretations. First, you can see GNN as a standard GNN with some embedding layer that comes from GBDT. So GBDT provides you new node features for the model. Or on the other hand, you can see this as a GBDT model that works on the node features, but now your GNN, it acts as a parametric loss function for GBDT. Now, with the experiments, we have tried to verify that this approach works on node classification and regression tests. We used mostly datasets with heterogeneous node features, and we used some of them with homogeneous node features to see what performance it gives on such datasets. We included the baselines with different types of GNN, GBDT, and also graph agnostic neural networks such as MLP. And we ran all the models from scratch with fair hyperparameter tuning, trying to get the best performance for each model. And this is the examples of the data sets that we use for node regression tasks. So for node regression, we try to predict a single number per node. And the features, for example, for the house, it includes the, as I said, the number of inhabitants, the area, geographical positions, and so on. For the node regression task, we have the following results. So 4 of the data sets have heterogeneous features. And we have the methods on the left. So we have GBDT approaches, which is XGboost and LightGBM. We have 4 different GNN architectures. We have fully convolutional, fully connected neural network, and also a fully connected neural network that is trained together with GNN. So we included this method in order to compare it against when we have GBDT first and then GNN. So we want to see if GBDT actually brings some performance uplift. And then we have two other methods, which is decoupled approach, which we call the REST-GNN or residual GNN. And then we have Boost-GNN model, which is the main contribution of the paper. And the performance results are here. So it's RMSE metric that we look at, and also the gap in percentages with respect to the graph attention network. So we try to see if the models improve over graph attention network, and if yes, by how much. So for 4 heterogeneous data sets that we considered, the performance uplift is quite significant. So it's 8% for house, 13% for the county data set with respect to graph attention network. And you can see, so the smaller this number, the better, because we want to reduce the RMSE error. And you can see that for heterogeneous data set, our models achieve the top results, the top 2 results. And for homogeneous data set, which is the Wikipedia data sets where each feature is, the node features are the back of words for each Wikipedia article, we get somewhat close performance for REST-GNN and a little bit worse performance for BGNN. So there are various conclusions for this result that we see that when you have the node features which are homogeneous, for example, back of words or pre-trained embeddings, then in this case, GNNs work really well. And when the node features are different in type and scale, then using BGNN can be the way to go. We have similar performance for node classification. So we have 4 homogeneous data sets, and 4 heterogeneous data sets and 1 homogeneous data set. And the insights here are very similar. So BGNN performs the best for 3 out of 5 data sets with very significant uplift. So in this case, we consider the metric accuracy. And so the higher this number, the higher the gap, the better. So we can see that sometimes we achieve up to 18% of improvement over graph attention network. While for homogeneous data sets, again, this data set has pre-trained word embeddings as the features. So BGNN
Sergey, I think the audio cut out. Or is anyone else able to hear him?
I cannot hear him.
Oh, okay. All right. So let me tell him over Telegram. Hopefully he'll rejoin us in a few minutes here.
Hello, did you lose me?
Yeah, we did lose you, and please feel free to reshare your screen.
Yes.
I would probably rewind a minute and a half or something like that.
Okay, sorry. So which slide did we?
Not too much. I think we're good on. I think we're at node classification. Yeah. Yeah, we were here. I think. Yeah. Yeah, just rewind 2 minutes is perfectly fine. Yeah.
Okay. So we have node classification results as well. So in this case, we see similar results to node regression, GNN performs the best for 3 out of 5 data sets, sometimes achieving up to 18% of improvement in accuracy compared to graph attention network. And for OGB archive, which has pre-training word embeddings as the features, the results are suboptimal. They matches the graph attention network, but they don't bring any improvement. And we tried to do an experiment when we compare different GNN models. So we tried to see if the results hold for different types of GNN models. So when we use graph attention network, we have the yellow one, which corresponds to ResGNN, and the red one corresponds to BGNN. And we try to see what is the gap, what is the improvement over the pure vanilla GNN. So you can see that the red one is always below the yellow, which means that we achieve better gap for different GNN models. And yellow in turn is always better than the vanilla GNN model. So that's good. That shows that our paradigm is agnostic to the GNN architecture that you choose. Now, you can think that this model, this approach would be time consuming because we have GBDT and GNN coupled together, and therefore we now need to train 2 models instead of 1. But it turns out that this model actually converges much faster than other GNN models. So here we see the training time. So the time it takes to train each model for when you use early stopping. So when you see that the validation metric doesn't improve, you can stop early. And you can see that BGNN on the right, it takes 20 seconds on the house dataset, on the VK dataset to converge. While GNN models such as Graph Attention Network, GCN, AGNN, and APPNP, they take much longer. So sometimes 2 or 3 times more than what BGNN requires. And the reason for this is that we, as I said, we converge much faster. So here's an example when we have epochs at the bottom, and this is RMC error that we look at during the training. So we can see that this BGNN line at the bottom, it converges almost by the 10th epoch, so it converges very fast. While for GBDT and GNN models, usually takes hundreds of epochs or sometimes even more. So sometimes it takes thousands of epochs in order to converge to its optimal value. And for us, because we use GBDT at first, it gives us very good performance from the beginning. And then we kind of tune this performance with GNN in end-to-end manner. So thank you very much. This is all for me. If you have any questions, I'll be happy to address them.
Yeah, thank you, Sergey. Do we have any questions in the audience? Feel free to ask or type them in, and I can read it out to them.
Hi, Sergey. Leo from Graphistreet. So that was great. I was curious when you said about when you're showing the speed up time. Would a multi-GPU or anything like that speed up the training time as well, or that, like, how are you looking at that?
So we use GPUs to train GNN, so that definitely helps in terms of performance. And actually, by this work, I was surprised to see how much efficiency you get if you use GPUs to train GNNs. So the results were like, I think it was like 30 times faster to train GNN, but I think it's kind of for any GNN that you use with TGL, you get that performance efficiency uplift. For GBDT, we haven't found, so we can use GPUs with GBDT as well. So libraries such as XGboost or XGBM, they allow you to specify GPU. We have tried that, but it doesn't bring any efficiency when you use them. So overall, we use GPUs to train GNN for this model, and we didn't use it for XGboost and IGBM.
Now, one more there. Like I saw that the data sets were, I think the bigger ones were like 100 or 200,000 nodes or edges, which is actually great relative to some of the other data sets we've seen with other graph neural networks. But let's say we want to go to like 1 million or 10 million or like 1 billion. Can you comment on that?
Sure. So I think the answer to this is that so our model is actually agnostic, as I said, to GPT and GNN models. So for GPT, handling big data sizes is not a problem. So as long as you can compose the node features that you can plug into GPT, that's fine. And GPTs are now used in production in different companies. So the co-author of this paper is from Yandex, and they use XGboost as the production model for their search and many products inside the companies. Therefore, GPT is fully capable to be distributed and to process large data sets. Now, GNNs, as we know, it's more challenging to scale, but again, you can plug in here any GNN model. It doesn't care about a particular architecture. So, for example, you could use probably Sign from Stein's team or any others GNN that are efficient and that can take as input X prime and G and gives you some predictions. Therefore, it should be, in theory, capable to learn good functions for larger data sets. I don't see any problem as long as you're ready to engineer this distributed settings for your data.
Yeah, thanks. That helps.
Any other questions? I think there was a question prior that said, Sergey, it would be great if you could explain what edges are in those graphs. I think this must have been one of the earlier slides. Maybe slide, yeah, might be number 4. Yeah.
So the edges, I give here just examples of the graphs. So it depends on the particular data set. For molecules, we have data set between atoms, and these edges have also the type, and sometimes it has additional features. But it would depend on a particular data set. So each data set usually model the graph as relationship between some entities. And here we consider kind of homogeneous graphs in the sense that each entity is the same, has the same meaning. So for example, it could be atom, and relationship is just bonds between atoms, or social network where we have the edges, like how different people are related. Or for GB archive, I think it's if 2 papers cite each other, then we have an edge.
Okay, I think that's all the time we have. Again, I want to thank you, Sergey, for taking the time to present today. And I did put his user group address in the chat window here. And he, I think that's on Telegram there, and he regularly posts very good resources and papers that's new. So I would encourage you to join that group on Telegram. I think it has about 2,300 users on there already. So Sergey and I work together in both the GNN user group as well as the group that he has created. So next up, we have Dr. Pan Li. He's a professor at Purdue University, and he is going to cover inductive representation learning of temporal networks via casual anonymous walks. So, Dr. Lee, you have the floor. Let me know if you have problems sharing the screen.
No. So thanks, Wenming, for the nice introduction. Yeah. So so first, I feel great honor to be here and give the talk. So let me set up my slides and
it's at the very bottom.
Yeah.
There's a green button that says share screen.
Yeah. So give me 1 sec.
Yep.
This, I guess.
No problem. Yeah, thank you.
Yeah.
I'll let you.
So is that clear?
Perfect. We can see it.
Yeah,
Yeah,
cool,
it's perfect. Thank you.
So
you can just make it full screen, put it in presenter.
Is that a full screen? I think I'm using a full screen.
It's working now. Yeah, it's working now. Thank you.
Yeah. Okay, cool. So thanks everyone. So perhaps right now I'm in the East Coast, so right now it's a good evening. Yeah. So today first let me introduce myself a little bit. So my name is Pan Lee. So I just joined Purdue University as assistant professor actually last year, 2024. So my research interest is on machine learning and optimization. So both sides, and particularly particularly I focus on the graph related tasks like machine learning on graphs and large graph computation. So, but I'm more on the algorithmic side instead of system side. Yeah, so that's and my recent research is around graph neural networks. And particularly related to, I think my research is more on the theoretical thing related to graph neural networks. But I'm still interested in pushing forward using graph neural networks in different type of applications. Okay, and today I would like to introduce our current work, our recent work on representation learning of a temporal network. Okay, so this is a joint work with so my RA students in Stanford, Yanbang Wang, Yanyu Chang, and my current student Yunyu Liu in Purdue, and also Professor Yuri Leskovic is coordinating this project. All right, so we know that we are all graph fans, so we know there is a graph structural data are actually everywhere across the different domains in social science, in biology, in database, and etc. So it's a very complicated structure, and this is why we need to use a machine learning technique or particularly representation learning technique to extract the pattern there, so that we can use it for, let's say, further prediction or try to understand of data better in some better way. And so today we will even focus on maybe an even more complicated data structure, that is a temporal network. So so in the temporal network, we have temporal networks are usually the abstractions of very complex dynamic systems. Usually each node here correspond to some interacting elements in the system, and the edges in the temporal network correspond to the interactions. Okay, and temporal networks just means, okay, here we have something or some properties of the network will change over time. Okay, and according to different type of definition, so typically temporal network can be grouped into two categories. The first one is that we the network structure will not change, and only the node attributes or edge attributes will change over time. And for example, like a traffic network or power grids are example like this. And the second type of temporal network is we may expect the network structure also to also change over time. Okay, also change over time, and this will be our today's focus. Okay, so particularly we will focus on the case when the network structure will evolve over time. Okay, And okay, so to motivate our problem, or so first I would like to review some basic concept we have known from network science regarding related to temporal networks. Okay, and this is very important motivation behind our model. Okay, behind our model. So actually, in network science, people investigated this temporal network for quite a long time. It's always a very important research topic. And actually, if you check most of the network science papers, you will see people just would like to investigate whether there's some fundamental laws or rules of different type of networks, and that correspond to different type of dynamic systems. And here I mentioned the fundamental laws means that dynamic systems will change over time, will evolve over time according to some laws that are universally appeared in a network. Okay, universally appears in the networks. And here I give a bunch of examples. So actually, there are very important laws in a temporal network. So the first one is something called Triadic Loader. So it's a fundamental law in social networks. So typically correspond. So it has an explanation that is in social network. When two people have some common friends, they tend to know each other in the future. Okay, they tend to know each other in the future. And this is Triadic Loader. And of course, it's very simple. Okay, maybe more, a little bit more complex pattern in the temporal network is called this feed-forward control loop. Okay, so this pattern widely appeared in biological and engineering control system. So it usually corresponds to a feedback mechanism. Okay, so for example, here you have an element, let's say W, that will stimulate the generation of another element U, and you want to guarantee this system to be stable. So what they will do is later this W will also stimulate another element, let's say V, and V will somehow prohibit the generation of U a little bit. And in this way, we can guarantee this dynamic system to be stable in some sense. And because of that, so this kind of feed-forward control loop appears quite often in biological control system and engineering control system. And okay, so we know actually these are very simple laws, and we may expect more complicated ones. And then our idea is this. So our representation. So right now we want to represent temporal networks. So we have this question. We know this temporal networks have this fundamental laws. We're wondering whether we can build a model that can learn or extract these laws so that we can better our the representation of a temporal network. Okay, so whether we can, let's say, indeed capture this laws so that it can help us to make some prediction of how the temporal network will evolve in the future. Okay, so this is we naturally have this question. So because of this, the previous understanding in the network science. Okay, so perhaps one thing is it's kind of related to maybe a very widely discussed task, which is called link prediction. But I would say it's more than that. So in link prediction, people always consider, okay, before a certain time, we have already observed this graph structure there. So we want to predict whether there's a link between these two nodes. But I would like to say, so our task is a little bit more than that. So kind of more than that. So we want to, our model can indeed capture some laws of this network. So how let's say, how can we evaluate that? So we must emphasize the inductive capability or the generalization capability of the model. So think about that. So if your model indeed captures that laws, that a type of laws, so this model should not only make a right link prediction over the original graph, it also should do a very good job over some new graph that also satisfy the same law. For example, if you train your network over social network, so you let's say train your model over social network and it indeed captures this triadic loader, you expect your model still work on another social network. Okay, so this is why I argue. So actually, our task is more a little bit more than link prediction. Okay, and so in particular, we will emphasize a lot about this inductive or anonymization. Okay, but I have to say this task is actually rather challenging. So so for next several slides, let me review a little bit about how so what type of temporal network representation learning model we have right now, and why is the task here is challenging for them. Okay, so there are a lot of temporal networks just works on something called network snapshots. So what they do is just aggregate this let's say this edges that appears over time into different snapshots, okay, into different snapshots, and then we will have a series of networks or graphs here, and then they will try to combine, let's say, a graph neural network or GNN model with some sequential model together to make the prediction of how it evolved in maybe in a future snapshot, okay, and so this is so this is covers a lot of works, but today our focus is not on this. We focus on another setting, so we will not do this snapshot aggregation. So but later our analysis is still can be applied to this network snapshot setting. Okay, so but our focus later will be this continuous time model. You can view what you observed is a sequence of edges, and they appeared in a continuous time space. Okay, continuous time space. And indeed, there is a few works on this, but they have some issues to solve this previous problem, or let's say inductive representation learning of a temporal network. And why is that? So first, let's so for these three works, this direct, Jody, and the TGN. So what they do is actually quite natural. Just follow our intuition about this temporal network. What they have is they will have a memory to track every node representations or every node embeddings. And for example, if we ask this model a query like whether there is a link between U and V at the time t, so what this model will do is they will find let's say search or just select the node embeddings of node U and V and maybe their neighbors, and try to run a GNN model on maybe GAT or different type of thing. It doesn't matter, and then makes this link prediction. Okay, combine this two node embeddings and make the prediction. And once they do this prediction, and if there indeed a match or link observed between this U and V, they will kind of update the node representations of U and V, and then record them into this memory. Okay, into this memory. So this is their line. So it's very natural. Just to follow our intuition, because our node embeddings is more like a summary of all the historical behaviors regarding this node. Okay, quite natural. But I have to say this model has some risk to represent let's say fundamental laws of temporal networks. So for example, here I give an example, like let's think about oppositional law. So we want to let's say we want to solve the following task. So we have a student and we want to predict whether he or she would like to purchase a car right now, and where he or she wants to purchase that car. And perhaps a very natural law in our mind, or inductive bias in our mind, is like this. So this student got admitted by a college, okay, and he or she did some summer intern. He or she has some salary, and then because she has some salary, and she also he or she get admitted by the college, she has some need to purchase a car, so she may purchase a car. Okay, and he or she will purchase that car in the city of that college. okay, of that college. So this is some, let's say, some intuition in our mind. And okay, think about this. So suppose our model let's say, try to learn this behavior by using, let's say, students in US. Okay, so for example, something like here. So it try to train on Tom, and who is from New York, and suppose our model indeed observed this sequence. So Tom get admitted by the college, and also do some summer intern, and Tom may would like to purchase a car. Okay, so in New York City. Suppose our model trained like this, and we want to say our model, whether our model can be used to, let's say, make inference on the students, let's say in, I don't know, in UK. Okay, so I have to say, so there is some risk for this model to do this job. Why is that? So because we can imagine, so these two, let's say Mike and Tom, may have some node embeddings, okay, that's memorized by the memory, okay, or recorded by the memory, and they will not be the same, okay, they will not be the same, because no people, let's say, there are not two people over the world have all the same history, okay, so they will not be the same. And although our let's say models observe this behavior, so and we may expect, because of the initial embedding of Mike and Tom are different, so so although our model trained over Tom, so when we use our model evaluate on Mike, and Mike also follows the behavior exactly the same as a Tom here, the output will be different, because this initial node embedding are different, okay, because of this initial node embedding are different. And this actually so this actually limited the generalization capability of our model, okay. So another way to understand this is more like this. So suppose you have a bunch of nodes embeddings. Let's say these right nodes are node embeddings in the training data set, and that represent the history regarding this node. And and actually this when you, let's say, use your model over some testing data set, you may encounter some node embeddings like this green node that are totally different from this, let's say, red node, okay, totally different from this red node. And although maybe later this red node and green node share some similar, let's say, behavior, okay, but our neural network, because neural network is just we all know they are over parameterized, and they are very sensitive to the small perturbation, and their output actually could be very different. Okay, could be very different, and this gives us some limitation when we want to have a generalizable, let's say, node generalizable representation here. Okay, so this is the problem. So any questions regarding this? No, so let me continue. Maybe we can keep the question in the end. All right, and okay, so this is the problem about the model that will let's say record node embeddings for the temporal network. So there is some risk. And another problems, let's say another model that can claim to do this temporal network representation learning is this Tigal model. So actually in this Tigal model, Dr. Xu actually was aware of this problem. So in his model, he will not memorize the node representation anymore. Okay, so what they do is just like this. So if you have a query to predict whether there's a link between U and V at a certain time, so what they do is just do some randomly sampling of the history related to node U and V, and then run the GNN model over this stuff. It's just like the original version of graph stage. You can imagine like this. So we do some sample of their neighbors, or maybe even 2 hop neighbors, and run the GNN model to aggregate them together to have this node U and V. I call it temporal embeddings, okay, temporal embeddings, and then use this embedding to make a prediction, Okay, so there's no memory here. And indeed, this model, okay, solves the previous problem I just mentioned because they don't need to track the node embeddings. But it actually runs into some other problem that we called ambiguity issue. Okay, ambiguity issue. So this model, this issue is some fundamental issue regarding neural network representation power. Okay, so even in a static network, you also observed this. So when we generalize this model to the temporal network, so this problem appears again. So that is this. So suppose, here is an example. Suppose we have two node pairs, okay, AB and A prime B prime, okay, and we observed some events, the similar type of events or links in either of the pair, okay. So at T1 and T2 time, we observe the links between A and B, and at T1 and T2 time, we also observe links between A prime and B prime. Then our question is, at T3 time, if I ask node B, okay, would you like to have a link with A, or would you like to have a link with A prime? Okay, so let's say, based on our intuition, so we should say, okay, B will definitely interact with A, right? Because they have a lot of, they know each other in history, right? They tend to get interacted with A instead of A prime. But unfortunately, if you use Tigal model, you will see Tigal model essentially cannot distinguish A and A prime. Okay, and here I draw the figure here about a potential sampled neighbors based on Tigal here. So if you check here, so if you have this node A, sample is history neighbors, you have B here, because there are the two links, you can have this graph structure. And for the A prime, you also have this. And right now, if you set, let's say, all the nodes with the same node representation, of course, this this representation for node A and the node representation for node A prime will be exactly the same. Okay, you run into, so Tigal model runs into this ambiguity issue. And suppose if we set the nodes with different, let's say, node features or representations, then the model reduced to, let's say, the previous TGN direct type of model. So so if we, let's say, if we distinguish them, this node features here, so they may have some inductive issue. Okay, they may have some inductive issue. So because of we observed this, so we claim that Tigal only works for the case when you have let's say very effective and inductive node features. Otherwise, Tigal will fail. Okay, otherwise Tigal will fail. So this is my argument on this. And okay, so because of this, we observe this issue. We think whether we can solve this problem in a very fundamental way. So this gives us this causal anonymous work idea. So our idea is still inspired by the previous observation in network science. So we know there are a lot of fundamental laws, and actually these fundamental laws are can be viewed as temporal network evolving. And then our idea is, if we can properly represent these temporal networks, then we can solve this problem. Okay, then we can solve this problem. The only challenging question here is, how can we efficiently represent or encode these temporal networks? Okay. Okay. So if some audience here are not familiar with temporal networks means connected subgraphs that consist of that edges that appears within a restricted time range. Okay, restricted time range. So you can view it like a graph pattern or subgraph pattern here in the temporal graph. And our idea is, okay, if we can represent or capture this temporal networks pattern, then we can solve this problem in an inductive way. Okay, in the inductive way. And a naive way to encode temporal networks is just to do, let's say, we can enumerate all the temporal networks in the graph and then construct a vector over that and then make a prediction. But there is a fundamental issue for this. So it's too complex. Okay, it's too complex, especially in the temporal network, because each edge may appear several times. And also, if you want to count the temporal networks or count a type of network motifs, you need to solve a graph isomorphism problem. Okay, so this is very complex. And actually, our causal anonymous work can be later you can see is a way to much more efficiently to represent this temporal networks. Okay. And okay, so then what's our procedure to solve this let's say temporal network motif representation? So this causal anonymous work follows two steps. The first step is we just do some random sampling of let's say random walks over this temporal networks. So how can we do that? Suppose we have a query, let's say between U and V at time 10. We want to say whether there's a link between these two. So then we will start from U and V and do some random walks. Okay, do some random walks to collect this random walks over the graph. And of course, here we require this random walks to follow something we call causality. So that's because so we require this random walks will be backtracked over time. Okay, will be backtracked over time. And this you can view this procedure as a subsampling of the potential temporal network motifs. Okay, because each random walk here corresponds to a network motif. And because we are doing subsampling, so this will be a much more efficient. This will be much more efficient. Okay, and in practice, we actually see that you actually don't need to do much for each node. Maybe you just need to do maybe 30 to 50 random walk sampling. Then that's enough to give you a very good performance. Okay, and okay, so that's the first step. And the second step is, okay, so right now for each node here, we have a bunch of random walks. So then we need to think of a way to encode these random walks, but we cannot, let's say, keep the original node identities. Otherwise, the model is still not inductive. Okay, so because if you train on a model, you change to another one, so then you train on a network and you evaluate it on another network, then the node identity will totally be different. Okay, will be entirely different. And then, but the problem is if we remove the node identity here, the random walk itself has nothing. Okay, only some time steps. Okay, other than time steps, there's no other information. And how can we solve that problem? So this is our step 2. So the key idea here is we will replace the node identity by using something called relative node identity. Okay, so for example, and this relative node identity, you can view it like a counts or the numbers of a certain node that appears at a certain position in this sampled random walks. Okay, for example, like this B, we want to compute the relative node identity. How can we do that? So in this sampled random walk, so we find, okay, at the second place, B appears 2 times. At the third place, B appears a single time. So then this will give us this vector. So it's a 0, 2, 1, 0. And in this set, B only appears in the at this last step for only once. So this vector is a 0, 0, 0, 1, and then we combine them together, and this will be the relative node identity for the node B. And then once we have this node relative node identities for each of the nodes that appears on the walk, we will switch that back to, we call it this procedure as anonymization. Then we transform the original random walks into another anonymized random walks, okay, into another anonymized random walks. And you can imagine this relative node identity here somehow keep the structure, graph structure here, or keep the motif structure here, okay? And this is actually the key innovation in our method, because previously people also used some anonymous walk method to compute the network embedding, but the way to do this anonymization is totally different, and only our way can capture the motif structures, and previous ones cannot. Okay, cannot. So especially try to measure the correlation between the different motifs. And actually, how can we come up with this idea is because it's inspired by one of our previous work, which is called distance encoding, that accepted by Neurons 2020. So in that paper, we theoretically proved that how this let's say relative node identities helps to improve graph neural network representation power. And even before that, actually another model, which is called SAIL, and so they want to do the link prediction over the static network, and they actually benefit from a similar type of strategy. Okay, the similar type of strategy, which is also a distance encoding technique. Okay. And all right, so right now we have, you can think about what kind of data we have. We have this anonymized random walk, actually a set of anonymized random walk. And then what we do is just encode this walk. Then it's very easy. So very simple model can do it here. So we just run RNN here to encode each walk and then aggregate them together. We will have the node representation, okay? And we use this node representation to make the final prediction, okay? So that's our model, and all right, and so why this let's say this model can work? Maybe I want to let me see if I have enough time. Maybe I can skip this part a little bit, and later I will go back if you have questions. So that part. Give you some example why our model can be inductive and why our model can solve the problem that Tigal model cannot solve. So that ambiguity issue. Okay, let's first see some let's say experiments here. So we want to test our experiments in both, let's say, transductive setting and inductive setting. So in the transductive setting, it's the same. It's the same case as before. We will only have one network, and we will evaluate on this train our model on this network by using the first partial of the edges and test it over the remaining edges. And in the inductive setting, we will hold out a part of the network and train our model over the remaining network and try to evaluate our model over the let's say the test network, okay, or the part of the network that are held out during the training procedure, okay. And here is the performance. And first, we actually extensively evaluated different models. Here you can have this see this transductive setting and the inductive setting. And just as we predicted, so if you use a model to record this node representation, such as this Direct and Jody, you can see a significant drop in their generalization or inductive capability performance. Okay, so there is a big gap between this inductive setting and transductive setting by using this Direct and Jody, and which depend on this node representation memorization. Okay, and if we use Tigal model, okay, just as we predict, it has some good, let's say, generalization property. Okay, so there's no big gap from the transductive to inductive setting. But the problem is, if it works, if we test this model over the network without effective node and edge features, even in the training data set, the performance will be very bad. Okay, will be very bad because of the ambiguity issue. Okay, because of the ambiguity issue. And what actually our previous serial understanding cannot well explain is this TGN model. So although this TGN model also, so it's more like a parallel work. In our original paper, when we wrote this paper, we were not aware of this work, but later after our work paper got accepted, we also try to evaluate this model. But actually, although TGN model also let's say track node representations, it still has some relatively reasonable inductive performance. so which is kind of out of our expectation. So maybe in the future we can look into that a little bit. But even it has this good generalization property, so it's still so in most of cases, still our CAW work still outperform this TGNN model. Okay, TGNN model. And yeah, so that's the result. And of course, our model is not perfect. Maybe some of you have already been aware of the potential issue of the CAW model. So all of the issue we think is regarding its computation. So because for each queried node pairs, so we need the current CAW pipeline need to sample works, okay, random works. And although we may prove, okay, you only need to pay constant complexity in theory, but you can view that constant complexity is still, that constant is still large, okay, is still large. And moreover, we need to compute that relative node identity. So, and which is also has a certain complexity. And right now, we, according to our CPU, let's say time complexity evaluation, I think our model is more efficient than TGAT model, but slower than TGN and Jody. Okay, so those models that memorize the node representations, and this is our issue. And right now we are working on a new pipeline that try to accelerate the computation of the CAW model. And our idea is based on some incremental way to update CAW. So not for every queried node pair we need to do a sampling there, but we will update this node representation, let's say this sampling procedure and this relative node identity computation in let's say in an incremental way, so that we may expect some computation efficiency gain. Okay, here. Okay, let me just give a summary of this work. So we actually, so the motivation of this work comes from the regional network science. We know all the temporal networks have some fundamental laws. And if we may capture those laws, we may represent this temporal network in a better way. Okay, and how can we solve this? We have this idea, and how can we implement that? So we propose this causal anonymous walk idea. So that is, we will sample the random walks around the node pair that we are caring about, and we propose a novel way to encode this temporal networks. Okay, this temporal random walks. Okay, and our performance, the performance of our model is actually significantly better than all previous baselines. But right now the model is still have some computational issue, and I know most of the audience here today are maybe more from let's say system side, and you are all experts on computation. So I guess I suppose maybe you can provide us some good suggestion to further accelerate the model. So although right now we have some idea, but yes, it's still ongoing work. Okay, it's still ongoing work. And thanks for your attention, and that's all for my presentation.
All right, we have 5 minutes for questions.
Mm-hmm.
It looks like there's a question in the chat window. Hi, Dr. Lee. You named your work as Casual AW. May I know what's the difference between CAW or Casual Random Walk versus AW? Do you conduct any casual inferences?
Yeah. So this
causal
is
inferences. Sorry. Yeah.
Yeah. So this is the next question. So first thing is originally. So actually, the key part I have to mention is not, let's say, causality. Okay. So first, I have to say our model do not use any formal causal inference features here. Okay. Do not use any formal causal inference features here. And why? But why we call our model causal anonymous walk? The reason is because we work on temporal network. Okay, and the way we extract this random walks is to backtrack it over time. Okay, it must satisfy some logic here, and this is why we call it causal anonymous walk. But indeed, we do not incorporate any causality information. Okay, and let's say any further causality information. Okay, but the main difference between CAW and AW is not this part. The main difference between the two is about this this anonymization part. Okay, and what's let's say AW does is for each work. So it will do anonymization for each work independently. Okay, so in the AW, but in our case, we want to capture a more let's say complicated network motifs, and also establish the correlation between the random walks in the random walks rooted at node U and rooted at node V. So we have a join of this relative node identity. Okay, and essentially the key difference between CAW and AW is try to establish the correlation between different works and the works rooted at different nodes. Okay, so this is the difference. So in the AW, the anonymization is just for a particular node. Okay, so this is my answer. Yeah.
Yeah, there's another question. It's from Leo. He says, I didn't understand the node encoding. So every node becomes a vector of length sample plus whatever attributes plus sample encoding for its neighbors. If so, how big is the samples per iteration?
Let me try to understand here. Oh no. Yeah. So thanks for your question. So so this, let's say this vector here, the length of this vector is only related to the length of random walks. Okay, the length of random walks instead of how many samples we want to do. Okay, so it's only related to the length of random walks. And actually in practice, this length of random walks is actually very short. So it's just 2 or 3 is usually enough to give you a very good job. So basically this vector here, the length of the vector here is just 2 or 3 dimension. Okay, with 2 or 3 dimension, it's very short. It's not related to the number of random walks we need to sample. And typically in practice, how many random walks we need to sample for a link prediction? In our evaluation, we typically sampled 30 to 50 random walks to perform this link prediction. So this is my answer. Yeah, so Ellie have a question. So sorry, maybe Leo. So do you have any further question regarding my answer?
I'm good. I'm gonna have to look at it for a little bit to see a few examples.
Yeah. Sorry. So sorry, perhaps I missed some part. Okay, so Ellie have a question like, is there any continuity assumption on the network over time? Does the loss of your model inference implies this continuity? Actually, we don't make any assumption of this. Okay, we don't make any assumption of this. So it could be, let's say, not continuous, and it's fine. Yeah, we don't have that assumption. We don't have this assumption, and our laws also do not depend on. I think do not depend on continuity. Although link prediction is typically related to a continuous graph. So for example, like this triadic loader procedure and feed-forward control loops. So although they related to the continuity of this network, but our model do not make that assumption.
Okay, I think that's all the questions we have. And again, I want to thank you, Dr. Lee, for taking the time to chat with us today.
Yeah.
I'll, it turns out that I do have an interesting project that would be able to use this. We have some lightning sensors that are that could potentially use this network. But anyway, I wanted to maybe open up the floor for, there looks like there's another question.
Yeah, sure, I can share my screen.
Let's see, occurs. Okay.
The node encoding the
signal. He's just, he's just saying that,
Yeah.
Okay, I do have a couple of announcements. One is that I think the OGB folks at KDD Cups 2021 wanted us to make an announcement that the deadline is, team registration is, let me actually paste this. Let me share my screen real quick. Can everyone see my screen?
Yep.
Okay, great. So the OGB folks says that for the we're actually helping to sponsor some of the compute. So KDD Cup 2021, the deadlines are coming up, and that's today's for some of you. That's and that's tomorrow for those of us who are in the later time zones. So the team registration deadline is April 30th, and May 10th is the initial test submission. So definitely reach out to this, to the organizers if you have any questions. I'll put the link in the chat window here. Let's see, chat window here. And another thing I wanted to point out is that the MLSys user group had a workshop. It's the GNN workshop. So this was essentially the agenda. There were quite a few interesting talks at the workshop. So I'll make these available as soon as they're actually released for Slide Live. The reason it's delayed is because we had AI Stats and a few other conferences kind of back to back. So by next week, we should have these available, and I'll announce them on the Slack channel, in the general Slack channel. Anything else that anyone would like to share? So I put the link to the OGB submission timeline in the chat window here. So feel free to take a look at it. Anything else anyone would like to share? We're good? Okay, so I guess I'll see everybody in the next user group meeting. If there are suggestions and things where you would like to actually see, feel free to reach out to me directly on a Slack channel. We'll be happy to arrange that. And if you have talks that we would like to present to the group, feel free to reach out to me as well. Again, I want to thank all of you for taking the time to attend. And just hope everyone have a good rest of the evening.
Thanks,
All right,
thanks. Great
See you
talks.
next time.
Thank you.
Bye. I'll have the recordings ready when my computer finishes processing it. Thank you.
Thank you, Wenming. So